Good afternoon, everyone. My name is Ian Sherrington, and I'm Director of the Just Institute for Tribal Technology. I'm also a member of the Tribology Group Committee of the Institution of Mechanical Engineers, and as part of that responsibility, I organise these everyday tribology webinars. These webinars are intended to highlight the important role that tribology has in our everyday lives and how it improves it. And in the past, we've had presentations on the lubrication of bicycles, tribology of chocolate, tribology of wine, and so on. Today's presentation is on the tribology of mechanical watches, and many of us will have a watch and perhaps haven't thought about the kind of things that go on inside that watch. So today we have Professor Tomasz Liskiewicz, who is Professor of Tribology and Surface Engineering and Head of the Department of Engineering at Manchester Metropolitan University, to tell us about these things. He's got 25 years of international experience across a range of countries, including France, Canada, and Poland, and his work focuses on tribology and surface engineering and functional surfaces. He holds a PhD from École Centrale de Lyon, and he is a fellow of the Institution of Mechanical Engineers and a principal fellow of the Higher Education Academy. He also serves as editor-in-chief of Tribology Materials and Surfaces and leads the initiative Surface Ventures, which many of you will have heard of, while also chairing a STEM racing activity in Poland. Thomas, we're looking forward to listening to what you have to say. Please share your screen.
Thank you so much, Ian, for your introduction, and I'm delighted to have the opportunity to talk on this subject, which is absolutely fascinating. So the most popular watch is in the world currently is Apple Watch. So we are not going to talk about Apple Watch today. When we look at any analog watch, like those on the screens, we might realize that this is a quartz watch. So we are not going to talk about quartz watches neither today. We are going to talk about mechanical watches, which might look like this one here, like this lovely Baltic classic watch, which has look-through back case, just to make sure that the owner can admire the inner workings of this watch. So what I want to do today is to talk a little bit about the historical context to watchmaking. I want to mention about more contemporary innovations, sprinkle a little bit of horological education, and of course there will be tribology theme going throughout all that. Right, before we go any further, I would like to ask you the question, which type of watch, if any, are you currently wearing? So is it a smartwatch like an Apple Watch? Is it quartz watch, mechanical watch, or maybe you're not wearing a watch at all? So thank you for all the answers which are coming through. I didn't know what to expect at all from that poll, but the results are indeed really interesting. I think you will be able to see the results at some point, but basically it seems like there is a very even split between the four answers. So at this point we have 27% for smartwatch, 22% for quartz, mechanical is 30%, and I'm not wearing watch 33%. So the majority of you are wearing mechanical watch today, which is amazing. That's and of course you are in the right place. Right. So thank you for that. So perhaps my next slide for 30% of you won't be that interesting or applicable, but for the rest, I just want to very quickly go through how does the mechanical watch work. So on the top of the screen, you can see a diagram highlighting the key components of the watch, and below you can see a photograph of the actual movement. The energy in the mechanical watch is stored in a wound mainspring, which you can see on the left here in green, which is sitting in spring barrel. And the mainspring releases torque and energy through a gear train depicted in yellow gold in the middle, which is regulating the speed. Then underneath with a pink, two pink components is the escapement, which converts the continuous rotation into precise oscillations of the watch. And this is the sound that you might hear from the mechanical watch. Then you have the balance wheel, which oscillates at fixed frequency, setting the beat of the watch. And eventually the hands move via the reduction gears, translating those oscillations into move of the hands and time. I realize that there might be a cohort of you that maybe are not familiar with tribology. So just quick 2 slides about what tribology is. The word tribology itself comes from a Greek word tribos, which means rubbing, and ology, which of course means the study of. So tribology is the study of rubbing, or the study of things that are in relative motion. It covers the fields of friction, lubrication, and wear. And the formal definition of tribology is the science and engineering of understanding friction, lubrication, and wear phenomena for interacting surfaces in relative motion. So in order for tribological processes to take place, we need 2 events. We need, or 2 components. We need 2 surfaces which are put together, and then there needs to be some relative motion generated between them. And this is exactly what is depicted in this cartoon when I am asked to describe what tribology is using one slide. Usually this is my go-to figure, which was produced by my colleagues a few years ago, and it really captures and encapsulates all the processes taking place at the sliding interface between 2 components at the tribological interface. So you can see the nature and the number of different mechanical, physical, and chemical processes taking place during that interaction of surfaces. So this is really beautifully complex picture, which keeps us tribologists busy. So a little bit of horological education. I want to start with watch complications. So watch complications is really any function of display of watch beyond hours, minutes, and seconds. So these additional features require extra parts and components within the mechanism, and those can range from simple date display to more sophisticated perpetual calendars, chronographs, moon phases, and so on. So those examples of 3 watches that you can see on the screen, on the left, the Baltic watch doesn't have any complication. The PSOT PRX in the middle has 1 complication, as it is showing the day of the month. And the lovely Patek Philippe on the right has 4 complications. It's also showing the date of the month, but also it's indicating the actual month, also the day of the week, and it has the moon phase complication. So that leads me to my next question, which is how many complications do you think has the most complicated wristwatch? So how many complications? I just showed you an example of a watch with 1 complication, with 4 complications, but how many complications you think the most complicated wristwatch has? So thanks for your votes, which are coming through. Yeah, yeah. Okay, so looks like that all of you answered. Thank you for that. Thank you for your engagement. So 11 complications answer is not very popular. It only has 12% of votes, but you can see that the most popular is 21, but actually the correct answer is 41 complications. 41 complications. So let me show actually that watch. So a watch with 41 complications is this Vacheron Constantin Solaria ultra great complication La Premiere watch. It's a lovely piece. You can see how it looks like from outside with all those basically every possible area and part of the dial on the front as well as at the back is occupied by some sort of display and complication. But what is most important, of course, is how this is achieved through mechanics and inner workings of the watch. And you can only imagine how complicated that watch must be in order to achieve all those complications and display them on the dial. So incredibly complicated watch. It has 5 very rare astronomical functions, also has innovated Westminster minute repeater, and looking at that movement there on the right-hand side, it has 1,521 components put together to deliver that incredible watch. And apparently, in the process of making of that watch, there were 13 patent applications filed as a result of that project. Okay, before we move on to mechanical watches, I just wanted to give you a quick context how time was measured before there were first mechanical clocks and then watches invented and produced. I had an opportunity to actually see some of those examples in a lovely museum, Seiko Museum in Tokyo, which I would very much recommend, where on display there are some sundials, water clocks, and combustion clocks. So I think we are all very familiar with sundials invented by ancient Egyptians around 5000 BC. However, as we know, sundials are quite useless on a cloudy day, at night, and of course cannot be used indoors. So the problem with that was solved again in Egypt around 1400 BC by making water gradually flowing from a vessel at a constant rate. And the time can be with that measured by change in the water level. The combustion clocks are known to have been used in Buddhist temples since 8th century. And a combustion clock uses material that can provide constant rate of combustion to measure passage of time. And as you can imagine, various materials have been used in this way, such as candles, lamps, and match cords. But moving on to mechanics and early beginnings, the mechanical clocks first appeared in Europe around 1400 century, with early examples like a clock in Milan in 1337, and this Salisbury Cathedral clock that you can see on the screen, which was produced in 1386. Actually, the Salisbury Cathedral clock is the oldest surviving working mechanical clock. So I would very much recommend you to go to the cathedral and see it yourself in the area. So these clocks relied on basic mechanical gearings and bearings, and of course high friction between interacting surfaces very often led to rapid wear in inaccuracy of those movements and required very frequent manual adjustments. And tribological principles were applied for simple lubrication methods using animal fats, oils, to reduce and control that friction to some extent. Moving on to 16th, 17th century. This is the time. This is the time when first pocket watch was produced. But starting with the cartoon at the top of the slide, again from a Seiko museum, this cartoon shows how power sources had to be downsized from using dead weight, as you can see on the left there, to springs. And regulators improved accuracy, moving from very simplistic and large balance through pendulum to balance wheel. The first watches were really small clocks, and that was the movement from taking large clocks from the towers to the pockets. And the earliest known surviving pocket watch is believed to be produced and developed by Peter Heinlein around 1530 in Germany. Apparently, when Queen Elizabeth I of England died in 1603, she was said to have owned 11 watches, which maybe she wore on bracelet attached to her clothes. We don't really know. But the technological developments in that era led to specialization, where different people and workshops very much became expert in making separate part of the watch, like for example escapement, or cases, or dials, or hands, or maybe wheels and gears in the movement. An important part about this specialization is that it allowed mass production of similar parts. And this was in particular seen in Switzerland after the arrival of Huguenot nation, which was very specialized in making jewelry and also precision components, and this is depicted in the diagram on the left-hand side. Moving on to Enlightenment and 18th century, the improvements in quality of steel in the century enabled further accuracy and really miniaturization of clocks and watches. And this is the type that the development of maritime chronometer took place, and is considered the most representative contribution to horology during this period. And this topic requires some explanation, because the empirical and very imprecise methods in measuring time and distance traveled at sea led to many errors that repeatedly resulted in very dramatic shipwrecks. A clock that was only a few seconds too fast or too slow could result in ship ending up in several kilometers of the course. So this really led to the Longitude Act in 1714, where the English Parliament awarded a prize in money to whoever would find a precise method for the exact determination of point at sea by measuring time very precisely. And this brings a gentleman called John Harrison in the picture, who after much work and experimentation in 1761 was the first to actually develop a chronometer, a large pocket watch, which is shown on the left hand side, which during navigation between Plymouth and the island of Barbados measured the longitude with distance error of only 9.8 miles. And this, of course, allowed Harrison to win the Longitude Act prize. So that way, Harrison solved some of the tribological challenges, including how the rotating pallet rides over the escape tooth face and also its curved back. This time also marks a point where jewel bearings were introduced for the first time, and they replaced the metal-on-metal contacts, very severe tribological contacts, where jewels like rubies were used for control and low friction. That was also a time when a very established and well-known watchmaker, Abraham Louis Breguet, said to King Louis, for whom he was developing a watch piece, that if only he can give him a perfect oil, he will be able to return a perfect watch, really highlighting the importance and understanding of lubrication and tribological principles in watchmaking. So moving on to the 19th century, it's a time of industrialization, time of standardization and mass production of watches. The Swiss system didn't really lend itself to modern production methods following industrialization revolution, but instead the vast industrial powers of the USA transformed watchmaking into factory-led process, as is mostly today. And of course, Henry Ford's production line concept inspired some watchmakers such Waltham, Elgin, and others in the US, as they found ways to make pocket watches at very, very large scale. Some of these watches, I have to say, were of very low quality, not designed to be repaired, and many of them had even paper dials. However, there is an interesting side effect that took place in this time of this industrial scale watch production, which was dramatic improvement in precision machining and manufacturing of very, very small parts. And these tools were later used to make precise scientific instruments, such microscopes and measuring devices that changed the face of the modern science as we see it today. In this period, in 1816, a gentleman called Louis Monet invented a chronograph, which required a very, very precise surface interactions to achieve the precision. Chronograph literally translates to time writer, but it essentially means a stopwatch, a very, very precise stopwatch. And Monet's pocket watch could measure time to 1/60th of a second. Moving on to modern era in the 20th century. There was rise in popularity in this time in wristwatch over pocket watch, and by 1930, the wristwatch had taken over 50% of the pocket watch market. In the 40s and 50s of that century, the chronograph wristwatch came back to popularity as the really practical use of watches in World War II. After the war, in the 50s and 60s, the space exploration brought wristwatches that could perform in very, very severe environments. And this includes, of course, very, very famous Omega Speedmaster watch. And then came what is called the quartz revolution or quartz crisis. In 1969, Seiko launched the very first quartz wristwatch in the world. Its technology, the quartz technology, was at least 100 times more accurate and cheaper than mechanical watches. And of course, with that, it brought the accurate timekeeping within reach of all consumers around the world. But by 1978, quartz watches had taken mechanical watches in popularity and really, really plunged the Swiss watch industry into deep crisis. And it's said that around 1,000 Swiss brands went out of business during that time. And this graph at the bottom there is capturing the nature of that crisis. If you look at the volume of watches produced in Switzerland, represented in yellow, you will see that from the peak in 1970, it dropped down very, very quickly to below 20 million in 1980. However, if you look at the value of those watches produced, this trend is not visible, which means that the Swiss watchmaking industry shifted to precision and luxury watches rather than mass production of cheaper watches. And the trend in terms of value produced is continuing growing until today. And 1908 was the year that the Rolex was founded, hence the early poster from Rolex there. Right. So this graph is kind of summarizing the watchmaking industry and market over years, starting from 1790 to 1984 in terms of volume of world watch production expressed in percentages. So I think I want to highlight just three kind of periods here. So in early ages, in 1790, you can see that the Britain was the dominant producer, producing around 50% of all watches produced in the world at that point. Then from 1870 to around 1940, there is a rapid growth of the mass-produced watches in the United States, and with that, the number of watches produced in Switzerland is going down. And then around 1970, we can see new markets in Hong Kong, China, and Japan producing more and more watches, with other markets, maybe apart from Germany, going down. It's worthwhile mentioning that these are percentages. So if we want to look at the actual number of watches, the 38% output from Switzerland in 1790 equals to 150,000 watches, and 6% output from Switzerland in 1984 equals to 39 million watches. So you can, with those numbers, you can imagine the overall growth of the output of world watch production. Right. So moving on to closer to the home, to the UK market. How many active UK-based watches exist today? How many do you think active UK-based watches brands exist today? Really interesting answers. So it seems like that, well, not seems like, but by a big margin, the most popular answer is less than 40. And then equally popular is answer between 60 and 80 and over 80, but only at 5%. Let me share the results with you. So less than 40, 69%, and 40 to 80, 21, and then 5 and 5. So I'm really happy to tell you that actually answer D is correct answer. Answer D, over 80, and I think it is easily over 100. So looking just at the British Watch and Clock Makers Organization, which represents the industry in the UK, they are currently representing over 100 UK-based brands as a trade body, and this number is really changing on, I would say, monthly basis, with new brands coming up. So really vibrant community, and the industry is said to experience a surging wave of optimism and energy with new brands emerging. One point I want to make is that we are not talking about a luxury and very expensive products. Of course, some of the watches can be expensive and some of the brands are very expensive, but this is not the case for all of the brands because you can purchase a really, really nice mechanical watch starting from maybe £200. And these are really, really nice pieces. So this is very, very inclusive and very, very vibrant community. Coming back to British watch and clock makers, they organize annual events. The next one will be taking place in London on 7th of March. And I think they will have over 50 brands, UK brands represented there. Okay, so in the last segment of my presentation, I want to touch on the contemporary innovations in watchmaking. So new materials are really finding place in the creation of wristwatches. They often take inspiration from other high performance industries like aeronautics or maybe F1 racing, and watch brand experiment with new materials, looking for lighter components, looking for strength and hardness, and also reducing need for lubrication, but also with some new designs and redefined and refined mechanics. So let me start with composites and ceramic materials. Carbon fiber, of course, dominates composite use in watchmaking. Like the example of the on the left from Gerard Perregaux carbon glass concept watch. And this tightly bundled microfibers can really outperform steel by at least order of magnitude, while in the same time weighing only a fraction of the weight. But beyond carbon, watchmakers also explore wider family of composite materials, typically some polymers embedded in epoxy resins for weight reduction. For ceramic materials, there are very, very in high demand in watch world because they offer everything that a sophisticated timepiece might need, which is high hardness, which is corrosion resistance, which is providing light weight, and also nowadays different colors, like for example zirconium oxide ceramic from Hublot. Also, those ceramics are offering very, very high hardness that can reach 1200 Vickers. But as a trade-off, of course, they are quite brittle, and the milling process can be quite challenging. In terms of alloys, titanium is the most common aerospace material that finds its way to watches. Of course, it's lighter than steel. It's also more anti-magnetic and more durable than steel. It can scratch like other metals, but because of its natural and very, very unique oxidation process, smaller scratches can become less visible over time, which is quite important for the watch cases. There are two downsides, however, to titanium. First, there is a higher price, of course, comparing to steel. And second, the finish, as titanium has this very, very unique and distinctive gray look that for some collectors is advantageous, but others maybe don't appreciate it that much. And as you can imagine, there is a wide variety of different specially developed alloys used by manufacturers, and some brands combine precious metals with practical ones to create alloy that can bring best of both worlds. So creating hard wearing alloy that maybe also balance the luxury look, like this example of IWC watch with armor gold alloy, especially developed for this watch. Silicon is really interesting material in watchmaking, especially from the tribological perspective. We tribologists realize and know that pure silicon is not very good low friction material. However, it can function as very well under specific conditions, and particularly in microscale systems like watch movements. And this is why silicon is very popular in high-end mechanical movements because offers this unique combination of properties like low friction coefficient, high hardness, low density, anti-magnetic properties, chemical inertness, and also is easy to fabricate in terms of those small components. Moving on to coatings, those examples of watches on the screen are showing the application and use of DLC, diamond-like carbon coating, for decorative purposes, just to achieve a nice black matte finish of the case, or maybe dial, or maybe hands. And the DLC is quite popular in watchmaking industry, like other PVD coatings, like titanium nitride for the unique gold finish, or maybe chrome nitride for silver finish. It's worth spending just a couple of minutes on the escapement mechanism, and just to give you one example of how companies innovate in this space by understanding the tribological principles to improve accuracy and precision. So the Swiss lever escapement, we can call it a king in escapements, is the most popular escapement currently used, which we can find perhaps in 95% of mechanical watches. However, the sliding friction between the escape wheel tooth and the ruby pallets that you can see on the top of the screen there requires lubrication and requires a servicing every few years. Coaxial escapements are direct impulse escapements, and those escapements have none of the scraping actions, those abrasive actions, as the force in the escapement is delivered directly from the escape wheels to the balance. So by appropriate design of the escapement, this very civil tribological interface and interaction been avoided. But for those familiar with recent news in watchmaking industry, might recall Rolex recently releasing a very new Dynapulse escapement as a part of their new watch release recently. And in this design, Rolex really perfected the mathematical equation of two planar escape wheels that effectively log by meshing one with another, which is shown in this cartoon. Apparently, it took around 10 years for Rolex to develop that new mechanism and get to that perfection. So in this case, the sliding friction that we experience in coaxial and Swiss lever escapement is replaced with this rolling motion, which we know will completely change the tribological interface and processes. We mentioned briefly about bearings and jewels in watches. So the original jewels were made out of diamond in early days. Today, these are of course synthetic materials like ruby or sapphire. Rubies rate 9 on the Morse hardness scale, while diamond scores 10. So these are really hard materials. When you look at the watch description specification, typically you would find information about how many jewels are used in the movement, with the higher number of jewels representing better quality and more precise watch. I think currently the movement with the largest number of jewels is this Lion Son watch shown on the left, which has 78 rubies used in that watch movement. However, there were attempts to use ball bearings instead of jewels in the watch movements. On the right, you can see Eterna's Sphero drive system, which by use of ball bearings is minimizing gear train friction in the movement. These are not very popular, but there were some attempts to use ball bearings. A really interesting example of using lubricating principles in watchmaking and watch design is the Renaissance watch, which has this ROX module, which is entirely enclosed in oil. So the upper part of the watch is completely immersed in oil. And all parts are suspended in the liquid and therefore constantly lubricated, resulting in very low friction between the parts. This is perhaps not the main reason why the oil was used in this watch, as you can see on the left, because the liquid fills the top part of the watch. You are getting this very unique and very special presentation of the dial without any edges, as the oil that fills that part completely changed the visual aspects of the watch dial. Okay, so that brings me to my final question, and again a little bit of education. So a mechanical watch certified by COSC, which is Control Officiels use the chronometers, must achieve to one of those precision bands, if you like, in terms of by how many seconds the watch can be off time, if you like, per day. So 4 different ranges there, from -2 + 1 second to -2 + 40 seconds. Okay, thank you for your answers. And by far the most popular answer is the correct answer, which is -4 to +6 seconds per day. So very well done. That's the precision required for the watch to achieve the officially certified chronometer distinction. So very well done. Okay, so before I summarize, well, actually, after I summarize, I have some resources for you. So let me do this before I go any further. So what I wanted to achieve in this short presentation is that, in my view, and not only my view, tribology is critical aspect in watchmaking, and it has huge impact on precision performance of the timepieces, and some of them we discussed today. Friction and wear will limit accuracy and longevity, hence it's so important to understand the tribological principles and optimize those tribological interfaces. And when we look at tribological context, those major leaps in timekeeping required solving some of those tribological challenges. Hence, again, Breguet's quote that with perfect oil, the perfect watch can be produced. And I think this is very appropriate to summarize that short presentation. So I just have a few resources for you to follow up. If you wish to, I will direct you to a few academic research papers if you want to gain a better understanding of research done in this area. I have to say, considering the number of manufacturers and brands around the world, the scientific and research output produced and, well, published is very, very low. So there is not much research being released to the open, to the public domain. There is only a handful of papers that you can find on this subject. One example is this paper by colleagues from Switzerland and France, where they described Swiss lever escapement and look at the tribological interfaces in this mechanism. If you would like to look at some books on the subject, I have 4 to get you going. The first one is really unique piece, which is presenting 100 selected and curated watches that were produced over the last 100 years, and it's an excellent and beautiful way of familiarizing yourself with watchmaking, but also a history, and it really gives them perspective on the progress and innovation in this area over years. A beautiful book from Rebecca Struers, who is a watchmaker herself, who wrote a book of history of time, and it reads really fantastically. I very recommend. If you would like to flip through some nice photograph and see nice watches from different brands, there is a number of those books, but the watch shown on the slide is certainly a good starting point. And if you want to get a bit more technical, or actually very technical, Watchmaking but by George Daniels is absolute classic. I cannot recommend this enough. If you happens to be in London, you absolutely need to go to the Museum of Science and visit the Clock Masters of London exhibition. This is the oldest clock and watch museum in the world, and the exhibition is absolutely breathtaking. And the number and the nature of pieces collecting there is very unique. I have some photo credits for reference there. But with that, I wanted to thank you for your attention. There are my contact details there with some QR codes taking you to my LinkedIn profile and my university profile if you would like to reach out to me and discuss anything from what I presented today. So thank you all for tuning in today, and I handing back to Ian, I think.
Thank you very much, Thomas. Thank you for sharing your passion for mechanical watches with you. Before we finish, though, we have an opportunity for the audience to pass on some questions, and 1 or 2 are coming through. If I could please invite you to use the Q&A button at the bottom of your screen. If you just hover your mouse down towards the bottom of the screen, the buttons will pop up and you can enter your questions in the Q&A section there. Already I have a few questions, so perhaps I can introduce a few of these. One of the common interests seems to be about the lubricants that are used in watches. And I wonder if you could tell us, Thomas, about what kinds of classes of lubricants are used within a watch, and what developments there might have been in that topic, perhaps over time and then perhaps most recently.
Yes, thanks, Ian. So, as you can imagine, this is a very specialized industry that produces oils and greases specifically for those applications, and the number of types of different lubricants is really wide, because they are designed specifically for a certain parts of the movement, and there will be different lubricant used in the escapement, different used on gears, different used on bearings, and for all of those you need different properties like viscosity and so on. So there is a very wide range of different lubricants that specialized companies provide to the manufacturers. In terms of latest developments, I would say it's mainly in solid lubrication space. For us tribologists, we came across lubricants like molybdenum sulfide in other areas as well, but this is the one that is currently looked at in watchmaking, including some coatings like DLC coating.
Thank you. Another question. I was quite surprised myself to see how little was published on the topic of the science, if you like, and technology of managing friction in watches. And I can see that there's probably going to be quite limited energy in springs. Is it the case that people try to build models of the friction in these components, perhaps all together as a complete friction model, or independently in different small components of the watch, like the escapement? Do people do that? Is that kind of thing published?
I think I came across one paper on the model of Swiss lever escapement, only one, in the past, and I think it was done by, I think, enthusiasts rather than, rather this being a proper industrially funded research. So yes, that paper that I presented was a result of only one PhD thesis that I came across that is publicly available on the topic. So that particular work was sponsored by one of the biggest watch manufacturer in collaboration with the academic institution. Really interesting study, but I am absolutely certain that there are more of those studies, carried out in many places, but this is just not publicly available. This is just done inside the industry, and those results don't go out to be published. So this is well known that the big manufacturers, they have their own tribology, surface engineering, material specialists and teams. They have their own tribometers, and they develop in-house capabilities.
Thank you. Obviously, during your presentation, you covered some of the more recent coating technologies like DLC and titanium nitride, both for the operating parts and also for the aesthetic elements of the case and so on. But one of our audience would like to know: are there any cutting edge tribological developments in watchmaking that you're aware of that you've not discussed here? And then secondly, what are some of the major developments, direction of major developments happening now?
To best of my knowledge, I try to outline those latest developments and the directions in terms of alloys, ceramics, composites, and also coatings. So I don't think there is more than that, at least to my knowledge, and again, what is available in the public domain. So we would need to relate that to other areas and applications and typical challenges that we would see with coatings elsewhere. So that would be adhesion for certain, for PVD coatings, especially when those coatings are applied on bracelets and cases, as they can scratch, and maybe they can, there can be some spalling and a loss of cohesion. The only area maybe not mentioned that I know that is of interest are transparent oxide coatings applied on steel components, and this is for scratch protection. So they wouldn't add any aesthetic elements to how the watch looks like, but it would kind of provide this invisible protection from scratching of steel or maybe titanium components.
Thank you. Obviously, there's if you like, a level of competition between solid lubricants and liquid lubricants. And in the past, that you mentioned that there was this comment: "Give me the perfect lubricant, I'll give you the perfect watch." Could you discuss the advantages and disadvantages between using solid lubricants and liquid lubricants? And are there any parts that are clearly better lubricated by one arrangement than the other?
I think the general answer here, Ian, is that the industry is trying to get to the point where the movement doesn't need to be serviced by a user basically during their lifetime. So we are talking about 50 plus service time, service period for a watch movement. And we are not there yet. Typically, those watches need to be serviced every few years to be cleaned, to be re-oiled, and so on. So this is the challenge: how to get there without using very exotic and super expensive materials and technologies. And I think this is the challenge for the material science community, tribology community, lubricant formulation companies. So I think maybe I took that answer a little bit off the specific question you had, but I wanted to highlight kind of trend and direction of travel.
Thank you very much. We're coming up towards the hour now, so I'd like to thank Thomas for sharing his passion, both his passions actually, so passion for mechanical watches and passion for tribology and surface engineering with us today. I'd like to thank you as the audience for joining us over your lunch hour. I know there's a lot of people registered, over 200 people registered for this webinar, so it's nice to see so many people joining us. And it's a very international audience. I know that it ranged from New Zealand to the US, where I guess the time is not so convenient as it is for us here in the UK. So thanks for showing your interest. Thanks for joining us. And we look forward to seeing you at the next Everyday Tribology webinar. Thank you all.
Thank
Bye-bye.
you, Ian. Thank you all.